Hello viewers, welcome to this module on the properties of ordinary least squares estimates part 1. In the earlier modules we have seen at the techniques of estimation used to get the sample regression, and now in this module we will look at the properties arising out of the ordinary least squares estimates. So let us get going. The first property is that the ordinary least squares estimates are linear. We will see algebraically how the estimates turn out to be linear. Secondly, we will look at the unbiasedness property of the ordinary least squares estimates. And finally, we will look at the most important property, that is minimum variance. So, there are three broad aspects: linear, unbiased, and minimum variance. So, we will consider each at a time. First, let us look at the linearity property, and as earlier we will go through first the 3 variable model and then generalize the model to k variables. So, the 3 variable model is yi is equal to beta 1 plus beta 2 x2I plus beta 3 x3I plus ui, and already we have seen the estimates to be beta 2 hat is equal to y x2 summation x3 square minus y x3 summation x2 x3 all upon x2 square x3 square x2 x3 whole square, and needless to mention these all have the subscripts I for the ith observations, because the summations run from 1 to n, I running from 1 to n. Just for the sake of ease, let us denote the denominator by delta. So, we find that beta 2 hat is y x 2I times this expression, where x's are all non-stochastic. So, this expression which I just now marked out, we can write this whole expression as a weightage A. Similarly, when we look at y x3I, we find that it has a weightage given by this expression divided by this denominator, so that we can write this as minus b times summation y x3I, and that very clearly shows that beta 2 hat is linear in small y i's. It is linear in the small y i's. That is very clear, because A is summation x3 square divide delta and B is summation x2 x3 divide delta. If you want to go deeper into it, you can write this further as A summation capital Yi minus y bar times x2I minus B summation capital Yi minus y bar x 3I, which boils down to yi small x2i minus b summation yi small x3i. So, that is the evidence that the estimates are linear. With the help of the 3 variable model that we showed the linearity property. Now, let us generalize this to the k variable model. So, we know that in the k variable model we have y is equal to x beta plus mu, where y is of order n cross 1, beta is of order k cross 1, u also of order n cross 1, and here we have x of order n cross k. So, that is the regression model, which is estimated as y hat is equal to x beta hat, where beta hat, which is of order k cross 1, is given as x prime x inverse x prime y. So, again this is also linear in y. You can see that x prime x inverse is of order, it is of order k cross k. So, we can write this as some theta 1 1 theta 1 2 times theta 1 k, theta 2 1 theta 2 2 times theta 2 k, and finally theta k 1 theta k 2 times theta k k. So, that is our representation of x prime x inverse, and the second component x prime y will be x 1 prime y, x 2 prime y, so on, and x k prime y. So, that is the estimate of beta 1 hat, beta 2 hat through beta k hat. So, that is the estimate of beta given by beta hat, and of course, this can be written as summation x 1 I y summation x 2 I y and going up to summation x k I y with subscripts I everywhere, so that we can see that the second column vector again shows deeper into it the property of linearity. So, each of the beta hats is linear in the yi's. That explains the property that beta hat under ordinary least squares is linear in y. To look at the unbiasedness property of the linear estimates, again we take recourse to the 3 variable model. Unbiasedness means when we take expectations, that is the expected value of beta 2 hat will be equal to the true beta 2 in the population. So, the expectation of the estimate of the sample is equal to the parameter in the population. The proof is straightforward. Small yi is the difference between capital yi and y bar. This first expression is capital yi, where we replace it as beta 1 plus beta 2 x 2i plus beta 3 x 3i plus ui, and y bar is beta 1 plus beta 2 x 2 bar plus beta 3 x 3 bar minus u bar. That is the average of all these yi's. So, by definition, in deviation form, small yi is beta 2 small x 2i plus beta 3 small x 3i plus ui minus u bar. Taking expectations, we find that expectation of ui and expectation of u bar will be each equal to 0. Viewers, please recall the properties of the classical model, where we say that ui follows a statistical distribution with 0 mean. We have not yet specified the distribution, but the mean is equal to 0. So, expectation of ui is equal to 0, expectation of u bar is equal to 0. Therefore, expectation of yi is beta 2 x2i plus beta 3 x3i in deviation form. Now, if we take expectation of beta 2 hat and just substitute these values of expectation yi here and in the second term, and just write divide by delta, just as a shorthand form we are writing this as divide by delta. So, that is the expression for expectation of beta 2 hat, where we will substitute expectation yi as the first term. So, expectation yi is the term in the brackets multiplied by small x2i, the whole thing multiplied by summation x3i whole square, and then minus summation expectation yi is given as the term in the first bracket multiplied by x3i, and the whole thing multiplied by the product of x2i, x3i, and the entire numerator is divided by the term shown as delta. And now, if we collect like terms, you will find, if we focus on the beta 3 terms, you will find that this is beta 3 summation x3 x2 times summation x3 square, and here you have a minus sign. Once again you have beta 3 summation x3 square and summation x2 x3. So, the beta 3 terms get cancelled and we are left only with beta 2. So, that is beta 2 x2i square x3i square minus x2 x3 whole square divided by delta, but we already know that delta is the same as this term which multiplies beta 2. So, beta 2 times delta divided by delta is equal to beta 2. So, beta 2, and within the second brackets you have a term which is exactly equal to delta. So, therefore, that becomes equal to beta 2. So, that proves that expected value of beta 2 hat is equal to beta 2. So, now let us take a look at the unbiasedness property for the full k variable model. As we know that the estimate of beta is given by beta hat, which is x prime x inverse x prime y. Just to recall, what are these matrices x and x prime? So, x is this n cross k matrix, the first variable arranged vertically, n observations, so n rows, and k such variables, so k columns, that means n cross k, and x prime is nothing but the transpose of that. So, the first row, first column becomes the first row, and the kth column similarly becomes the kth row. And beta, viewers, for the k variable model is not a scalar, it is a vector, beta 1 through beta k. Similarly, u for the k variable model is not a scalar, it is a vector u1 u through up to un, that is for n observations we have n such random disturbance terms, each of this is a random disturbance term. And the property that we had for the classical model was that expectation of each of these ui's is equal to 0. So, with that backdrop we come back to the estimate. So, that is x prime x inverse x prime times x beta plus u, which simple matrix multiplication tells us that it comes to x prime x inverse x prime x beta plus x prime x inverse x prime u, and the multiplication of the first two expressions gives us the identity matrix. So, this becomes beta. The second one is written once again in the next line, x prime x inverse x prime u. Now, if we take expectations, we want to find out the expected value of beta hat. So, we put the expectations operator, beta is a parameter, so it remains as it is, and we apply the expectations parameter to the second expression, which is x prime x inverse x prime mu. But in this, within x prime u, within the second expression, it is only u that is stochastic. It is only the vector u which is stochastic. So, the expectations operator only applies to the vector u, and therefore, since we have already seen that expectation of u is equal to 0, therefore, expectation of beta hat is equal to beta. The basic idea is, if I have a sample, I get a value of beta hat. Similarly, other people may have other samples where x is fixed, but the values of y differ because of value of u. So, different people will have different values of beta hat. The average of all those beta hats will be actually equal to the true population parameter. That is the beauty of ordinary least squares estimates under the classical assumptions. Next, we will take a look at the fact that these estimates have minimum variance. We now take a look at the general version of the property of minimum variance linear unbiased estimator. We know that the population parameter in the regression is beta with k elements, k rows and 1 column. We have also seen that ordinary least squares method leads to linear unbiased estimator given by beta hat, which is also a k cross 1 vector. What is very remarkable is that under the classical assumptions, if we consider any other linear unbiased estimate, then the variance of those estimates will be higher than the variance of the ordinary least squares estimate. In other words, in the class of linear unbiased estimates, the ordinary least squares estimates have minimum variance. There can be different ways of developing linear unbiased estimates. Some may be very crude methods, others may be sophisticated methods, but whatever it is, among the class of linear unbiased estimates, the ordinary least squares estimates have the unique property that their variance is minimum. So, that means the estimates become more and more precise. On the average, expected beta hat will be equal to beta plus the variation will be minimum. So, we say that ordinary least squares estimates have minimum variance among all possible linear unbiased estimates. That means they are the best among the class of linear unbiased estimates. That is abbreviated as best linear unbiased estimate, or we call it BLUE. So, we say that OLS estimates are the best among linear unbiased estimates, but all of this will be true under classical assumptions. Viewers, now we will take a look at the Gauss-Markov theorem, which will prove that the ordinary least squares estimates have minimum variance among all other linear unbiased estimates. So, let us consider mu as a linear combination of the population parameters. Mu is a scalar which is a linear combination of the population parameters, because this beta is k cross 1 and c is a 1 cross k row vector. So, it is a linear combination. We want to first develop or propose an estimate of beta given by m. So, mu relates to the population, m is the estimate, and we should remember that we must have linear estimates. So, we are saying m is a prime y. As we have seen, estimate of mu is linear in y, just like estimate of beta was linear in y. So, for a combination of beta, the estimate of mu should be linear in y. So, that is our proposed estimate, and among linear estimates we have to consider only unbiased ones. So, for unbiasedness, expectation of m should be equal to mu, only then m is an unbiased estimate of mu. But what is m? M is a prime y. So, expectation of m is expectation of a prime y, which is equal to expectation of a prime x beta plus u, which is the model which gives us a prime x beta plus expectation a prime u, which is equal to 0, because expectation of u is equal to 0. So, the condition for unbiasedness is that this expectation of m, which comes out to be a prime x beta, this should be equal to c prime. So, for unbiasedness, this should be equal to c prime beta for unbiasedness. So, we are proposing a linear estimator, and we found out that in order for this linear estimator to be unbiased, it should be that c prime beta is equal to a prime x beta. So, to say the condition is c prime is equal to a prime x, or c is equal to x prime a. What about the variance of m? Variance of m is given as expectation of m minus a prime x beta times m minus a prime x beta prime, because these are scalars. So, square means we can multiply with the transpose, because this is a scalar, which is equal to expectation of a prime u prime a, which again becomes equal to expectation of a, rather we should put the expectation operator before u prime. So, a prime u prime a, which basically becomes sigma square a prime a, because expectation u prime is equal to sigma square I. That is the classical property, 0 covariance and homoscedasticity, absence of autocorrelation and homoscedasticity. So, that gives us variance of m is equal to sigma square times a prime a. So, we will minimize a prime a subject to the condition c is equal to x prime a, that means c minus x prime a multiplied by the Lagrange multipliers, and that should be equal to L. So, actually we minimize this, and there is a small technique that we will use. Since the derivative of this will become 2a, we will just balance, and since lambda is a Lagrangian multiplier, it makes no difference if we write twice lambda here. So, minimizing that, the first order conditions will become 2a minus, this is twice x times lambda whole prime times a. So, this will be x lambda with 2 in front. So, twice x lambda whole prime times a, x lambda whole prime times a, if we take the derivative it becomes x lambda, that should be equal to 0, which basically tells us that x lambda is equal to a, which implies x prime x lambda is equal to x prime a, which means lambda is equal to x prime x inverse x prime a. But from the first order condition we know that a is equal to x lambda. So, a will be equal to x times lambda, which is x times x prime x inverse x prime a, and we also know that x prime a is equal to c. So, that is equal to x into x prime x inverse c. Finally, what was our target? Our target was to arrive at a prime y. So, a prime y is therefore equal to the transpose of this times y, which is c prime x prime x inverse x prime y, and viewers, that gives us C prime times beta hat, because this term is nothing but our familiar ordinary least squares estimate. So, the result is, if you take any combination of betas and if you develop a linear estimate which is also unbiased, then the minimum variance will be arrived at only if the estimates of beta are the ordinary least squares estimates. That means, beta hat obtained through ordinary least squares has minimum variance among all the estimators in the class of linear unbiased estimates. For example, if we take C equal to 0, 0, 0, only 1 in the 5th position and all others 0, then this C prime will pick up only beta 5, because this is a fixed 5th position. So, this mu will be beta 5, and what is going to be the minimum variance linear unbiased estimator? The blue, the corresponding element, 5th element of beta hat, where beta hat comes from ordinary least squares estimates.